Good morning. More is coming in. Strange. So let's start, right? And hope everybody is doing well. And we didn't have any class meeting, but I want you to take that time to review for the extra credit, right? For review to figure out how to do that extra credit, right? I will, if you are having difficulties, let me know and I'll give you some more hints. I just want to give you, we will not give you the final answer. And here you go. Let's see. Exam is currently scheduled for May 17, right? Which is next Monday. Exam, let's see. No, next week.
Professor?
Not Monday, Wednesday next week, yes.
Sorry, we can't see your screen.
Oh yeah, let me, thank you. You know, now you can see it. Chat. And participants. Okay, so remember that. Let's see. Here we go. We are right here. We had no classes, no class. Just for I want you to think about that extra credit, how you're going to solve that, and I'm going to give you a little bit more of hints. Okay. What I want to do today is we're going to start chapter 25. Hopefully, we can get in chapter 26 too. Regarding chapter 24, okay, I decided not to cover polarization, okay? 24.6. So just concentrate on those 4 sections of the book. Hopefully, I'll be able to finish 25 today. If we finish 25 today, the exam will include the reflection and mirrors. That and that's chapter 25. Yeah, here you go. Reflection and mirrors. I am going to skip 25.1. I don't like the way they did it. We start with 25.2. Okay, then we go to 25.3. We're going to do 25.4. 25.5. Magnification equation, and 25.6. That's what I want to do for this chapter. Hopefully, we'll be able to finish everything today. And if we do, we leave 22, 23, 24, 25 for the exam. Going back to the syllabus, 23, see, 22, yeah, 22. We had only after, and let's not forget too, right? Which labs did we have? I shouldn't correct lab 5 and 6, so you don't have to worry about 5 and 6 this time, okay? And no class meetings. Yeah, I'll leave it for the final, lab 5 and 6. But I should be able to have it corrected. You know what? Until Wednesday, I'll have it corrected. Okay, labs 5 and 6. So until Wednesday, I'm gonna have it corrected so you can add it here. Lab 5 and 6. We are writing here. And that's any questions? Do you want to change the exam, or that's this is okay for you folks? I presume that there's no problem. It's okay. Okay, good. If you need to postpone, let me know, but let me know soon, right? Otherwise, I won't be able to. I will not be able to postpone it. It could be here. I'll be willing to put it on Monday, right? And then we do special relativity on Wednesday, right? We can do that on this other Monday, but that's going to be just a few days, 2 days before the final exam. You might not want to do that, but that's the option that's opened right now. Let's talk about ink again. We're not covering. Okay, we are. Oh, this. We're not covering polarization, right? 24.6. So you don't need to study this section. Reflection mirrors. 2, 3, 4, 5, and 6. Let's take a look at what we need to know about reflection and mirrors. The first thing you need to know, chapter 25. First thing you need to know is how light propagates from a source. Okay, that's the first thing you need to know. What you are doing here is also what we call geometrical optics, by the way. Geometrical optics, because it uses geometry to predict the behavior of light, reflections and mirrors. Geometrical optics. First thing you need to know is how light propagates from a source. I'm going to come up with an illustration here, how that happens. So let's start with a source, a point source. Here you go. The way light propagates from the source is going to be, that's one of the postulates of geometrical optics. Light propagates in straight lines. Okay, that's what we call the light ray. So this point source, it can also be an extended object. Okay, I'm gonna cover that, but let's start with the point source as the simple thing that we can have. Point light source. This point source can be a bulb, light bulb. It's going to emit the light rays that propagate away from the source. Okay. So it's going to propagate in this direction. So it's just like radial direction. That's the idea of light rays. And this is a very powerful idea. It explains lots of things in a very simple way. Format shape. Yeah, that's good. Let's change the arrow, right? Okay, this one right in here, like that. And then we're going to have this other light ray. Use all sorts of direction. And that's for the point source. If the source is not a point source, but is an extended object, and we can have those something like that. And every point in the surface of this object emits light. Okay, now we're going to have light coming out of every position of this object. Is going to be perpendicular, by the way, so the light doesn't interfere with the other. Okay, this is not a light source. This is not a point source. Okay. And we are going to be using this idea of light rays. Not just for this chapter, but for the next as well. Okay. That's a point source. So let's write it down here. Point source. Distributed source. Distribute light source. And now we are going to use this idea of light rays here for the case of a mirror. What you see right in here is the special case of the mirror, of the planar mirror, the one that everybody has at home, right? Reflection from a planar mirror. And now let's see, instead of reflection from a planar mirror, let's see, planar mirror. Let's just write down planar mirror. Reflection comes later on. Okay. And propagate from source. So here you go. Light can be in geometrical optics, okay? In geometrical optics, light can be represented by rays, okay? By rays of light. Let's put lowercase here, and I'm going to. This is a very good model. This is a very simple and good model for light, and it predicts, and it is capable of predicting. Different types of phenomena. Predicting and explaining different types of phenomena. Okay. Light propagates in a straight line, propagates in a straight line like rays. Okay. Now starting with mirrors, with reflection and mirrors and mirrors. Must know how light is reflected from a mirror. It's a very simple explanation, okay? How light interacts, I say, instead of reflected, how light interacts, how a light ray interacts with a mirror. Not reflects, but how it interacts with a mirror. There is a very simple law, which by the way is not a law, that's why I'm putting that between quotes, okay? Referred as the reflection law. Reflection law. The quote goes here. It's very easy to memorize this reflection law. The reflection law, and again, I will emphasize that it's not a law, it's just a consequence of something far more genetic, okay? It states that light reflects out of a mirror with an angle of reflection that is equal to the angle of incidence. Okay, let's illustrate that. You might not understand what that means, right? Or you may understand, right? Just sometimes, just by reading that, sometimes it's difficult to visualize exactly what it means. So let's go to the next level in case you didn't understand what I meant, right? Angle of reflection is equal to the angle of incidence. So here we go. If you have a point source, right, that's emitting a ray of light, there you go. Here's the ray of light of my, let's see here. Yeah, I can extend my mirror, right? Let's extend my mirror here. The law of reflection states that the angle of incidence of the light ray, here's my light ray coming out from my light source. Remember, this light ray there are several light rays here in this illustration because you have a point source. This light ray, I don't need that, has an angle of incidence right here, theta. I'm gonna exaggerate this angle. Let's exaggerate this angle, otherwise you're not going to understand it well. Let's put a little bit here to the top, right? So that's the angle of incidence. Let's see. I want to put it right in here. Yeah, that's good. That's the right place to put my angle, right? Angle of incidence, that's the angle of incidence right here. And I'll try to, I can make it even larger. So it's easier to see this guy and make it larger. Okay, must go up, 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 up. Right here. Angle of incidence. Black and thicker. Instead of black, let's put it red. And then I'm going to put a symbol here for angle that we usually use the theta angle. I'm going to put it symbol. And okay, so here you go. Incidence. Angle of incidence is equal to the angle of reflection. What does it mean? Okay, whatever light ray that's going to emerge right here is going to have the same angle. Reflection, rotation, reflection. Equal, reflection, that's not what I want. Okay, I gotta do that by hand. It's gonna have a reflection angle here that's equal to this angle of incidence. Right here, I'm gonna put it under a different color. Okay. Make sense? Can you memorize that? Easy enough to understand? Angle of reflection. I'm gonna make it a little bit thicker. Okay, that's what the law of reflection is all about. This light is going to interact with this mirror, and by interacting, it's going to be reflected, and it's going to be reflected in such a way that the angle of reflection is going to be equal to the angle of incidence. And I can do that step by step, right? So here we go. Incidence. The next slide is the angle of incidence. The next slide is the angle of reflection. This angle here. Is equal to this angle here. Let me erase that. Okay, and but this light, but this light source, it can also, send light in another direction, right? Here you go. Not only it's sending light in this direction, you can also send the light in this direction here as well. And all the time that sends light towards the mirror, the light is going to bounce back with an angle of reflection equal to the angle of incidence. And now And now that we stated that, by the way, here is a plane mirror, right? It's a planar surface. And the same principle applies to surfaces that are not planar. The book has a very good illustration here of a surface that's not planar. Here's a planar surface, but here is what we call a diffuse surface. It's possible to build mirrors like that. It is possible, okay? That's not completely planar, okay? And by the way, most mirrors are just like that. If you get yourself in front of a mirror very close, you see a very good straight image of yours. But because the surface of the mirror has some minor imperfections, just like what you see right in here, as you move further and further away from the surface of your mirror, your image becomes distorted, okay? Because you're getting all sorts of light rays that are being reflected at different angles, right? They're being reflected at different angles because of this ondulation here in the surface of the mirror. And even this ondulation obeys the law of reflection, specular reflection and diffuse reflection. So keep that in mind, okay? And now we can start talking, using this idea, we can now start talking about how images are formed. That's the reflection law states that light reflects, right, out of a mirror with an angle of reflection that's equal to the angle of incidence. This law applies both to ideal planar mirrors and mirror surfaces that are not planar. Okay, in the case of ideal planar mirrors, the reflection is said to be they're not planar and have several bumps along its surface. In the case of ideal planar mirror, the reflection from its surface is said to be a specular reflection. In the case of mirrors that are not planar, and have several bumps along its surface, the reflection is said to be diffuse reflection. In both cases, the reflection law applies. So here you go. So what are the ideas here that the new ideas I introduced to you? One, light ideas introduced so far. One, light behaves like a ray that propagates in the straight direction. Okay. And then we have the reflection law. Those are the two ideas that I have introduced you so far. They're the two important ideas that I have introduced to you so far. Now, let us use these two ideas to understand how an image is formed by a mirror, by a planar mirror. First by a planar mirror, and then we're gonna talk about other types of mirrors. It's a very simple procedure. Okay. So going here, I already have this illustration for you. So I'm going to concentrate on this one. Okay. I'm going to eliminate this light ray that you see right in here. And because I want to concentrate on this light ray. Okay. No, I got to put it back, that light ray here. Yeah, let's put back this light ray here. Okay. How do you determine the point of formation of the image? Okay. You extend the light ray that is reflected. What I'm doing here, remember, I have this light ray that reflects. I'm extending it past the mirror surface, and I have this other light ray here that's being reflected. I'm also extended past its surface. If I do it step by step, let's do it step by step, so you don't get confused, right? So here you go. I'm going to go back to this one here. I'm going to do everything all over again, right? I'm going now to come up with a second light ray coming out of my source. This light ray is going to be reflected at the same angle of incidence. Something around that, like that. Okay, and I'm going to draw them with different colors so you can keep track which light ray is which. This is one light ray. This is another light ray, and then you can have infinite light rays coming out from the source. Okay, so here you go. We have another one here that can come out from the source, and I'm going to draw it with a different color. Let's do that to blue. Yeah, let's do it blue. And then its reflected ray is going to be also a blue ray, and I don't need that guy anymore. Remember, even point sources, they emit light in every possible direction. If I did everything right, okay, sometimes we don't do it, but the angle of, don't forget, the angle of incidence should be equal to the angle of reflection, right? Third light ray. If I want to find the position of the image of this object here, all I have to do is to extend the light rays that are being extend past the mirror, right? The light rays that are being reflected. Okay, one here. Okay, I have to adjust to this angle here. Yeah, just a little bit more too, I know. Even more. Yeah, let's see. Here you go. Okay, so here you go. And this one too. I'm going to extend this one. Okay, and all those rays, they should intercept at the same spot, which is where the image of this object is formed. Okay, here's the image. The image of the object is formed behind the mirror. S prime. Okay. Make sense? We'll be using this technique for the rest of this chapter, and a similar technique for the next chapter. Okay. So in order, we're gonna write that down here. To determine the position of the image of an object, comma, you have to draw several, no, not several, but let's see, at least, right? You have to draw at least 2 light rays, at least 2 light rays coming out from the object. You have to do the following. You have to do the following. Let's see. To do the following. 1, draw at least 2 light rays coming out from the object. 2, those are the incident rays. These are the incident coming out from the object and propagating towards the mirror surface. These are the incident light rays. Okay. 2, draw the corresponding light rays that are being reflected from the mirror surface. Okay, that's the second step. And 3, extend the reflected light ray past the mirror surface. Okay. The position of the image behind, right behind the mirror will be the point where the 2 reflected light rays intersect. Okay, that's the procedure. I did the procedure in the drawing in a diagrammatic format here, and I spelled that out in the text in the notes. Okay. And here you go. We label the image as S prime. If you do everything right, we find out that the distance of this point to the mirror is going to be the same distance of its image to the mirror. This is already 25.3. Okay. And then we can repeat the same okay, not just for points of light, but also for extended objects. Here you go. Here you go. Instead of a point of light, consider you're sitting in front of the mirror, or standing, not sitting, standing in front of a mirror. Okay, and you are being represented by this arrow, by this upward arrow. I'm gonna do that in just like a movie, right? Okay, we have a mirror. And then we have the axis of a mirror. We don't need that yet. I'm going to erase that too, because, okay, start with the mirror. Put that right in here. to make the drawings, all the drawings simpler, right? Mirror, axis of the mirror. Do I need that? Let's see, what's this? Ah, okay, I don't need that. I don't need that. I don't need that. At least now, that's the axis of the mirror. I don't need that. And now I'm gonna put an object in front of the mirror, right? So here you go. Mirror, axis of the mirror. You need to draw all of that stuff to understand where the image is gonna fall. Object in front of the mirror. I'm gonna put my O in there. This object is a distance P from the mirror. And now I need that distance P from the mirror. And to make this drawing more easier to see, right? I'm gonna increase its increase its size, and I don't like this color. Yeah. Now, this distance we call P, position of the object. Let's see, let's make sure that okay, the book doesn't call it P, the book call it distance of the object, D sub O, okay? D sub O, let's go according to the book's notation. Subscript, distance of the object. Distance of the object. What do we have next? Okay, let's look at our first light ray. This one is not supposed to be here. I'm gonna draw my first light ray. Let's say my first light ray is the one that comes from the tip of the object and is incident in the mirror at an angle that is perpendicular. So I'm going to do like that. Here you go. Make it a little bit thicker. No, not this one. This one here. This one here. Okay. And because this light ray is incident, I chose this one. Okay. And all you need is two light rays to find out the position of this object. And then the reflected light ray is going to reflect in the opposite direction. Angle of incidence in this case is going to be 0 degrees. Consequently, the angle of reflection is going to be 0 degrees as well. Can you picture that? Right? There you go. I don't need that. There you go. Now you got it. I'm putting very close so you can understand what's going on, right? Angle light incident, light reflected. Light ray incident, light ray reflected. I'm gonna put in separate slides. And then again, Just like before, you're going to get a second light ray coming from this tip. Right, and here you go. Now we have, light incident, light reflected. Then you're going to come up with another ray, let's say the second ray. And this second light ray is going to be incident. Okay, I need another one here. The second light ray is going to be incident at this point of the mirror here, the center of the mirror. The intersection of the mirror is the axis of the mirror. When you have a, and again, I'm going to put in a different color so you can understand. This guy is not double arrowed. Good, it's like that. All right. One light ray, a second light ray. And then this second light ray is going to reflect at an angle that's equal to the angle of incidence. Okay. That's something you have to practice there at home. So now what do? You're going to extend the reflected light ray. Here you go. You're going to extend the reflected light ray like I'm doing here. Extend the first reflected light ray. Extend. You don't need that. I don't need that. Oh, this thing is, wow. All this junk here stayed behind. Huh? Good. So, mirror, axis of the mirror. Gotta go through those steps. Object, in front of the object, the distance DO, distance of the object. DO stands for distance of the object. Okay. First incident light ray, first reflected light ray. In this case, I choose a light ray that's parallel to the axis of the mirror. That's what we usually do. And then we choose another we choose another light ray that's incident at the center of the mirror and is reflected here at this point. Next, you extend the light ray. And now I can and then I extend this other second light ray. Okay. The position where those two light rays intersect is the point where the image of the tip of the arrow is formed. Remember, it's the tip of the arrow. And by the way, you can do the same for the bottom of the arrow. You're going to get a image format right here as well. And here you go. That is the, I'm going to denote this image by putting dashes. Okay. And we usually represent the image by the letter I. Another student coming in, 9:40. Okay. This distance we call the distance of the image. Distance of the object, distance of the image. Okay, what we find out is that this distance here for a planar mirror is the same as the distance of the object for a planar mirror. Okay, now, and I want to write that down here. D sub I is equal to D sub O. Sub I is equal to D sub O. If you want, you can do, more light rays than that. You can do a third light ray that's going incident here. If you do everything right, you're going to see that this third light ray will intercept at the same point that the other two intercepted. A fourth light ray and so on. Okay, I can erase that right now. Erase this one, erase this one. Good. 9:43. Let's review. Okay. First thing that you have to know is that a point source can be emit light in every possible direction. And a very good way of model light is by representing it by rays, light rays. In the case of a point source, light rays are being irradiated in every possible direction. And it happens not just to point sources, but also happens to distributed light sources, light bulbs that have a size, okay? And then using this idea of light ray, we can predict what would be the position of the image in a planar mirror and other types of mirror as well. So here you go. We start with a planar mirror. That's the samples of mirrors that we have out there. We put a source in front of the mirror, draw one light ray, use the reflection law to draw the reflection angle of this light ray and draw a second light ray. That's all you need. Just a second light ray. You don't need three to find out the final position, right, of the image. So let's erase this other light ray. Okay, so a third light ray is this one. If you want to know the position of the image of the source, all you have to do is to extend the light rays past behind the mirror. And then we have this image of the source that I denoted by S prime. You do the same for an object, not a point source, but an object, an extended object. Here you go, we have the mirror. You have to draw the axis of the mirror, very important. We're gonna keep on doing that all the time. And you put your object here, upright or down or upside down. And again, all you need are two light rays, not three, not four, not five. You draw the distance of the object to the mirror that I'm represented by DO, and draw my first light ray. We usually use light rays the first light ray that we use a light ray that's parallel to the axis of the mirror. And then this light ray reflects on itself. Okay. Then we draw a second light ray. We usually draw a light ray that's incident at the center of the mirror, whether it's a planar mirror or some other mirror. And the angle of reflection is equal to the angle of incidence. You extend these light rays, and this guy doesn't need to be like that. Yep. And we extend the second light ray. The intersection of those two light ray extensions is going to be where the image of the tip of the arrow is formed. In this case, the image is upright. And because the image is behind the mirror, we say that the image is virtual. Let's write it down. Okay. Images that are behind a mirror are said to be virtual. Okay. If the image is oriented in the same, if the image is oriented in the same direction as the object is, we say that this is a not right image. What you're going to do next is going to be a little something else that's a little bit more difficult to understand. But before we go into that, let's take attendance, and we're going to have our break, okay? Randy Bautista, are you there? I see Randy Bautista in my list. Hi, Randy. Well, he's not answering, so let me put a star here in his name. Vanessa Bonilla. Hi, Vanessa. You there? Oh, Vanessa's not answering either. That's next one, Ashley Diaz. Are you there, Ashley?
Yes, I'm here.
Thank you. Natalie Espinosa. I don't see Natalie here in my list. Nope. Jeanette Garcia. I don't see Jeanette either. Noor Hassan.
I'm here.
Thank you, Noor. Oh, Vanessa, right? Did Noor answer it? Jeanette Garcia is coming in. Hello, Noor. There.
Yeah, Professor, I'm here.
Okay, good. Thank you. Your voice came at the same time as Vanessa's message, so I was not sure. Okay, Blanca Hernandez. Are you there, Blanca? I don't hear Blanca answering. Oh, here you go. Thank you, Blanca. Next is Kaylee Hernandez. I saw Kaylee here, right? Good, thank you, Kaylee. Joshua Jimenez. I don't see Joshua here. Next is Alondra. Alondra, are you there? Alondra is usually the first one to show up here in my list, and I don't hear from her, so I'm gonna put a star. Let's see, Randy, are you there, Randy? Janet Garcia, okay. Janet Garcia, let me put attendance for you. Alondra is a star. Kennedy, are you there? Kennedy is always here.
Yes, Professor.
Thank you, Kennedy. Daisy Mariscal. Okay, so I'll get to you, Randy. Daisy, I don't see Daisy here. Yeah, Daisy is not here. Randy is here now. Alondra, we'll give you another chance, Alondra. Okay, next. Yesenia Montes Rodriguez. I don't see Yesenia here. Ryan Ong. Hi, Ryan, are you there? Thank you, Ryan. Artur Pacheco. Good. Next is Lebilud. Hi, Lebilud. Okay, thank you. Donia.
Here.
Thank you, Donia. Elika. I don't see Elika here. Okay. It is not here. Brianna Valencia. Thank you. Next, Justina Youssef. Is Justina here? No, I don't see Justina. And we have a total of 13, 14, 14. Yeah, the numbers match. And let's go for our break. Break from 9:52 to 10:07, right? There's no questions? Okay, so see you in a few minutes. I'm back. Now we are going to talk about the spherical mirrors. So let's take a look at, so first thing that we did, type of mirrors, right? Type of mirrors. One, planar mirrors, planar. And then we have this important type of mirror that is spherical mirrors. Planar mirror. Spherical mirrors. And then there are others, okay? In this course, we're going to do only those two types of mirrors. But if you go into, if you're going to make a living out of mirrors, right? You're going to study other types of mirrors. You're going to see parabolic mirrors. And then we also have hyperbolic mirrors, etc. There are all sorts of mirrors out there. But let's concentrate on the spherical mirrors right now. What is a spherical mirror? There's a name why you call it spherical. A spherical mirror is a section of a sphere, a hollow sphere. Think about that. Get a hollow sphere. You create a reflective surface inside this hollow sphere, and then you cut a little hub, right, out of this sphere. What you end up forming is a section of a sphere. What you end up forming is a spherical mirror. Most mirrors, I built spherical mirrors in the past out of glass. Okay, I did that, and we sell those things out there. Let me take a little break here. Okay, sorry, folks. Sharing and we sell. You know, we can buy those spherical mirrors very easily in any drugstore. Okay, they sell that, and we study this type of mirror. So let's see how they behave, right? Here you go. Here's the section of my spherical mirror. That's the center of curvature of the mirror, right? Which is coincides with the center of the sphere, of the spherical. We call the center, the distance from the center of curvature to the surface of the mirror, radius r. And I'm drawing here as well the tangent to the spherical surface of the mirror. So we're going to need that. Okay, there are some important, those spherical mirrors have some important optical properties. For instance, one very important optical property of a spherical mirror. If you have a light ray passing exactly through the center of curvature of the mirror, this light is going to be reflected into itself. The angle of incidence is going to be equal to the angle of reflection. In this specific case, the angle of incidence is 90 degrees with respect to the tangent, or 0 degrees with respect to the normal. Okay, so if there is an angle of incidence of 0 degrees with respect to the normal, then the angle of reflection is going to be 0 degrees as well. So a light ray that passes through the center of curvature is reflected back through the center of curvature as well. That's a very important property of spherical mirrors. Okay, let's write that down. Okay, spherical mirrors are mirrors that are formed from a section of the section of a sphere. Okay, if this sphere has a radius r, we say that the mirror also the mirror has a radius of curvature r as well. Okay. A light ray that passes through the center of curvature of the mirror is reflected on itself. Is reflected back to the center, right? Reflected back to the center of curvature. Here's an illustration of a spherical mirror in your book. Here you go. They took kind of a square section, right, of this sphere. And then there are other important properties. That's the first important property of a mirror, right? Optical properties of a spherical mirror. Optical properties of a spherical mirror. We go of spherical mirrors. Let me take the A out of it. One, light ray that an incident light ray that passes through the center of curvature is reflected back towards the center of curvature. That's the first property, but there are other properties very important. Okay, an incident light ray that is parallel to the principal axis, right? Principal axis of the mirror Not the principal. I call it to the axis of the mirror. Okay. Is reflected back towards a point halfway, roughly halfway between the center of curvature and the mirror. And by the way, that's not exactly true, but is reflected towards a point halfway between the center of curvature of the mirror, R/2. Okay. So we have an illustration here. Here's an illustration. See, light rays parallel to the axis of the mirror, reflected back through a point that is, halfway between the center of curvature and the surface of the mirror. Okay. That's and by the way, for now I'm just talking about concave mirrors, right? I have to specify here. Spherical mirrors are mirrors formed from the section of a sphere. This sphere has a radius r. We say that, okay. A light ray that passes through the center reflects back to the center of curvature of concave spherical mirrors. Let's start with concave first. Okay, there are two types of spherical mirrors, concave and convex, and that's what this drawing has here. A concave spherical mirror and a convex spherical mirror. Let's talk about the concave first, so you understand that better, and then we worry about other types of mirrors. Okay. There's another property of this type of mirror, and here you go. There's one property, right? And then axis of the mirror. The book call it principal axis of the mirror. Here you go, center of curvature, right? So here you go, light ray passing through the center of curvature, is reflected back, but light rays that are parallel, let's see here, that are parallel to the axis reflect towards a point here in the mirror that's half away. This point here is called the focal point. What you see right in here is the direction that is normal to the surface of the mirror. Normal to the surface of the mirror means perpendicular to the tangent of the mirror. This mirror has a diameter d. Okay. I'm going to, okay, when d is much greater than cc prime, okay, C prime is, C prime is this point right in here, okay, right in here. Much less than cc prime, then the light will intersect the axis of cc prime divided by 2. Okay, radius. This is called the focal point. And then what else? We can have something similar, right? Instead of light rays going through, passing parallel to the axis, we have a light ray that passes through this focal point and reflects back. So those are three important light rays that you have to have in mind. Okay. Oh, here you go. That's the one. Light rays. The axis of the mirror reflects, okay. An incident light ray that passes curvature of the mirror r divided by 2. This point is called the focal point. Focal point. We usually represent that by the capital letter F. And then conversely, an incident light ray that passes through the focal point F is reflected parallel to the axis of the mirror. Okay, so you have all those three important light rays that you have to memorize, and all those light rays obey the reflection law. All these light rays obey the reflection law. Okay. And then we also have that light ray that's incident at the center of the mirror. And it's reflected back with the same angle of incident. Recall that this surface has a curvature here, right? I'm not representing a curvature because it's too much work to do that. But this surface has a curvature here. That's why the light rays behave in this way that you see. Okay? So now that we know that, we can come up with a way to determine the position of an image formed by a concave mirror. Let's do that together. Here you go. We have, let's start with the mirror alone. Let's start with the mirror alone. Here you go. Okay, mirror. Axis of the mirror. We're playing the movie here, right? Next in line, you have to draw the center of curvature of the mirror. Here you go. Center of curvature of the mirror, right here. And then you have to draw the focal point of the mirror as well. Let's do that. Okay, focal point. Don't want you to see that yet. Let's go there to, this guy's not supposed to be here. This guy's supposed to be down there. Mirror, axis of the mirror, center of curvature, focal point, half the distance of the center of curvature. And then what I'm going to do next, I'm going to put an object in front of this mirror. And by the way, there are simulations out there that simulate very nicely this type of, in this case, your object is past the center of curvature, to the left of the center of curvature. I want you to figure out how to obtain the image of this object. You have to know that by heart. The first thing that I do is to draw a light ray that's parallel to the axis of the mirror. Every light ray parallel to the axis of the mirror reflects the light towards the focal point. Don't forget, this is just an approximation, but it's a very good approximation. The focal point is, again, is halfway between the mirror and the center of curvature. If the mirror has a center of curvature of 2 meters, the focal distance of the mirror is going to be 1 meter. Okay, so, and remember, I need only 2 light rays to find out, to determine the position of an image. Only 2. The second light ray, let's see, I will make it go through, let's get this one here, through the focal point. Okay, the second light ray is going to pass through the focal point. And though every light ray that passes through the focal point is reflected parallel to the axis of the mirror, like that. See, we already have a point of intersection here. Let's make sure that this drawing is parallel to the axis of the mirror. Let's see. Yeah, it is, right? Yeah, it is parallel to the axis of the mirror. So here you go. Now the intersection point here correspond to the point where the image is formed. So the problem here was not this. Okay, it's this one here. Let's see if we have. Yeah, I hope so. Let's see. More. Yeah, right in there. Now we have it right. But we're going to do a third light ray. So you can practice it, right? So you know that there are other ways. A third light ray is going to be that light ray that passes through the center of curvature. Okay. Yeah. I'm gonna move that. Here you go. Now I got it. Here you go. Reflected back. And if I do everything right, you know, this light ray should intersect exactly at the point where it's going through, okay? And finally, we draw the image. Here you go. My little arrow at that position of intersection of all those three light rays. Okay, three light rays, you know, all you need is two light rays, but it's always good to know what the other three light rays, or the third light ray does, right? What the third light ray does. This image here, here's the object, here's the image, right? This image here is said to be not a virtual one because it's in front of the mirror. It's said to be a real image. Okay. All these light rays obey the reflection law. Okay. If an image formed behind the mirror is virtual, comma, an image formed in front of the mirror is said to be real. Virtual, real, virtual versus real image. Okay. That's the principle that you should know. How you should know how to find those interesting images. Let's see what happens here. Oh, what else do I have to do here? I have to document the position of the object, right? Don't forget the position of the object. I'm gonna take advantage of that slide of the planar mirror. Okay. Here is you go. Here's the position of the object, distance of the object, and here is the distance of the image. But now the distance of the image is different from the distance of the object. Okay. Here you go. distance of the image. Like that. If you do, if you use geometry, we can come up with a very neat equation. Let's not forget, right? I didn't write that down, but it's better if I do something else here. Look at this focal distance, okay? The point here is the focal point, right? F, capital F stands for points. And then the distance of the focal point to the mirror this distance right here. Format shape. Is we represent with the letter F, lowercase f. Which is, by the way, c divided by 2. Focal distance, lowercase f. Focal point, uppercase f. Like that. That's what we need, so we don't need that anymore. And if you do all the math properly, I'm not going to derive it here. It's possible to relate all those distances in a very simple formula, by the way, that you can easily memorize. What is this formula? Let's go there tomorrow. This was image. Relation between F, D naught, and DI. Okay, so here goes F, D, O, and D, I. Okay, that's okay, is 1 over F, 1 over DO, plus 1 over DI. That's the relationship that you have to memorize. Oh, not memorize, right? But you can always look at the book. And there are lots of simulations out there in the internet. Spherical mirror simulations. Convex and concave mirrors. Let's see. Optical simulation, concave. Let's see if this one works well. Yeah, here you go. Okay, that's the object and that's the image, right? Notice that I'm going to start right now. Can I move it? Yeah, I can move it. Look here, I can increase the size of the object, right? And I can also move the object. Here you go. This object at 12, 13 units to the left of the mirror. Here you go, concave mirror. See the light ray parallel to the axis of the mirror is reflected back towards the focal point. this mirror has a center of curvature of 8 meters, let's say, and the focal distance is 4 meters, half of 8. The light ray that passed through the focal point is reflected parallel, and the light ray that passes through this center of curvature is reflected back to the center of curvature. All those 3 light rays, they should intersect at the same point. Okay? All those 3 light rays should be intersected at the same point. And notice how the behavior of this type of image, right? Let's say of the image of this object. As I get closer and closer to the center of curvature of the object, look what happens. The position of the image gets closer and closer to the position of the object. Exactly at the center of a curvature, the position of the image is equal to the position of the object. Not only the position, but also the size of the image. As we keep on moving to the right, okay, the image keep on increasing its distance. Not only increases its distance, but also the image increases its size. Okay, it starts with a smaller image, right? The more we move to the right, the larger it becomes. Past the point of curvature, it becomes larger than the object itself. When we go right here at the focal point, look at those light rays. Those light rays become parallel to each other. And no image is formed. We call it an improper image. Okay? As we go closer and closer to the mirror, and now the image that was real becomes a virtual image. Do you see here those dotted lines? You know, those 2 light rays are intersecting somewhere past the mirror. The closer we get to the mirror, okay, here you go. Here's the image forming it there. The smaller, the closer we get to the mirror, the smaller the image becomes. But the image is virtual now. The virtual image now. We can do all this math using that equation that you saw. Let us play with that equation. Okay, let's come up with an example. A very simple example, right? That reflects exactly what you saw. Okay. Example. An object. Let's see. A mirror. Let's start with a mirror. A mirror has a center of curvature of 2 meters. An object is placed at a distance of 4 meters. Find the position of the image. Okay, solution. Okay, so that should be simple, right? Simple enough. So let's just straightforward applications of formulas. Here is going to be 1 divided by 2 meters, right? 1 divided by 2 meters. 1 divided by 4 meters. And then we have this position of this image. So this one passes to the left. Okay. And I'm keeping the units there. I'm going to put everything under the same denominator. combine those two terms here, we end up with 1 divided by 4 meters. And then we invert this equation. We get that di is 4 meters. Okay. Now let's repeat that. Repeat, I want to even copy everything. A mirror has a center of curvature of 2 meters. An object is placed at a distance of 2 meters from the mirror, right? From the mirror. Find the position of the image. Now here's going to be 2 meters. Oh, wait a minute. I made a mistake here. Sorry, folks. Center of curvature of 2 meters means what? Means that the focal distance is 1 meter, right? Let's go back here. Example 1. Okay, don't forget, focal distance is 1 meter. Here's 1 meter. Okay, let's fix that. 1 meter. Let's see, 4. We end up with 4 here as well. And now 4 minus 1, we have 3. Okay, now we got 4/3. 4/3 of a meter. Now a mirror has a center of curvature of 2 meters. An object is placed at a distance 2 meters from the meter, okay, from the mirror. Now again, we're gonna have focal distance is 1 meter, 2 meters from the mirror. Here's 2 meters. So 1 meter, 2 meters, 1. Let's see, I gotta put 2 here. We have 2 divided into 2 minus 1 divided by 2 meters. 1 divided by 2. The I is 2. Okay. So the position of the image is the same. The distance of the image is going to be the same as that of the object. Okay. And let's keep on going. Here you go. What about a mirror has a center of curvature of 2 meters. An object is placed at a distance of 1 meter from the mirror now. Find the position of the image. Okay. Here now we have 1 meter. Okay. And look what's going to happen. We have those 2 terms that are going to cancel out. Okay, 1. 1 minus 1. Let's see. Okay, this minus this is going to be 0. Okay. It's going to be 0. And what does it mean? It means that the image, you invert this equation, right? It means that this image is formed at a distance that is very large. Now I can put it here. D goes to infinite. I need to find the infinity here. Oh, right in here, the very beginning. That's what we call this image is called improper. This image is called improper. Okay. That's exactly what you saw in that simulation, right? Let's go there again. Here you go. Object at the focal point. Okay. DO is 3.97, right? It's not exactly equal. Now DO is 4. Yeah, it's 4. DI is a very large number. See that? A very large number. There's a little difference between, it's not exactly 4. Oh, okay, now I got it. Now my DI is a question mark. Parallel rays. The rays are parallel. That's the improper image. Concave mirror, D naught is equal to F. Okay, let's save that. No, we don't need to save that. I'm going to put, so you can play with it. It's going to be very useful for the exam. See simulation. Simulation in. Okay. Right here, here's the link. Now let's keep on going. We're going to do another example. Now, instead of 1 meter, what happens if my object is placed a half meter from the mirror? Okay. The focal distance is still 1 meter. What changes here is this 1/2 meter. And now that we have 1/2 meter here, right? Look what's going to happen. Same denominator. We're going to get, I do not know if you already saw that, we're going to get a negative number. Okay. The I ends up being minus 1 meter. What does it mean? Oh, it means that the image is virtual. Negative distance means that the image is virtual. Let's get that right here. My mirror has a center of curvature. Let's see if I can get. I can't. No, unfortunately, doesn't look like I can adjust. Yeah, I cannot adjust. Unfortunately, I cannot adjust the center of curvature here, the distance. Okay, but so let's take a look here. Here you go. There's something like that. Okay. The image is on the other side. See, the distance of the image is negative. If the image is right, is real, the distance of, if the object is located past the focal point, its image is formed at a positive distance, so the image is real. But if the object is between the focal point and the mirror, the image that's formed is going to be virtual with a distance, with a negative distance. Okay, so those are the different types of things that you're going to see. For D naught greater than the center of the curvature, D naught equal to the center of let's see, D naught greater than the center of curvature, D naught equal to the center of a curvature, D naught between the focal distance and the center of curvature, and D naught at a position less than the center of curvature. Those are the important cases that you have to have in mind. Okay, 10:50. Any questions about that? So let's take a little break again, and then we're going to go for what we did. That was for, we did that for a concave spherical mirror. Next, we will cover the convex spherical mirror. Okay. It's 10:51 a.m. right now. We're going to have another 15 minutes break. That's going to be 06 a.m. Okay. So I see you in 15 minutes. I'm back here. Start sharing. Chat and participants. Good. So that's the concave mirror. Now let's talk about the convex mirror. But before we move, right, let's situate ourselves where we are here. Okay, ideas introduced so far. You go. Light behaves like a light ray that propagates in the straight direction. Okay, reflection law. Within the reflection law, we start talking about reflection from a planar mirror. Let's see. Now let's just put here planar mirrors. Planar mirrors. And then we start talking about spherical mirrors. Now, among the spherical mirrors, we have two types of mirror: the concave mirror, and the convex mirror. That's how it goes. It depends on the reflection law. The behavior of those mirrors depends on the reflection law. I'm sharing the screen, right? And we're going to cover. I think I should make it a little bit thinner, right? It doesn't. No, not this one. This one maybe. Here you go. No. Okay, yeah, better now. 2.25. Yeah, better now, right? Okay, well, at the end I had all that stuff here, but that is. Now, what about the convex mirror? That's the representation of the convex mirror. The representation of the concave mirror is this one here. Okay, that's the representation of the convex mirror. Every time we deal with mirror, we have to come up with the axis of the mirror, right? And then we go ahead and mark the points, the important points of the mirror. Here's the center of curvature. Because it's a convex mirror, the curvature is in this direction, right? It's no longer in this direction because the curvature in this direction. Now the center of curvature is past the mirror. The focal point is still going to be this one, and here's the, the opposite of the center of curvature. And then we have this focal point F prime as well. So if you're going to do it in the proper way, right? First we mark the center of curvature of the mirror. And then we mark, the opposite, right? The center of curvature of the mirror. And then the next is going to be the focal point. And finally, the other focal point F prime. Okay, so let's go. Let's put our object to the left of the mirror. That's the position of the object, right? That's the position of the object. And I want to take this one out. I'll take this one out too. So the drawing is not too busy. Put the object there. The next thing that we do is to document the distance of the object to the mirror. I'm using P, but in reality, the book, I want to use the notation of the book, which is D naught. I'm going to use this one here. D naught is not going to be P. One more student coming in. We go. Instead of P, we are using the notation D naught of the book. All right, that's gonna be an incident light ray. And this incident light ray is going to reflect in a different way. It's not gonna converge towards the focal point. Okay, it's not going to converge towards the focal point. It is going to diverge from the other focal point. Going to be something like that, right? A parallel ray is reflected away from the axis, whereas in the case of a concave mirror, in the case of a convex mirror, parallel ray is reflected towards the axis. And now we can come up with the extension. Okay. Those are the rules. If you want to find out and then we have, remember, we need only 2 light rays. And what be one of them? One of them would be the light ray that's incident towards the focal point. Okay, so here we go. See, this light ray that you see here is incident towards the focal point. Why is it doing that? Anybody knows how to, let's see. layout, paste. Oh, it's strange. I never know how to remove those things here when they appear, you know. Happens in Excel, happens in PowerPoint. The set slide. No, that's not what I want. Okay, looks like it's okay. It's fixed the problem, right? Here you go. Even better. Here's this light ray that is reflecting towards the focal point. Right? That's incident towards the focal point, right? I'm extending this light ray to the focal point F prime there. And this light ray that you see right here is going to reflect parallel to the axis. That's why I put it here. Okay. And do you see this extended light ray? It intersects with the first light ray. That's where the image is formed. And by the way, there is this other one too, that one that's reflected, you know, at the same angle, right? Let's do that. Okay. If I did everything right, so we finally have our image. Yeah. Formed behind the mirror, and because it's formed behind the mirror, that's called a virtual image. And this distance that you see here, go distance of the image. Okay, so I don't need that anymore. Let's take a look how it looks in a simulation. There you go, concave mirror. Let's see. Concave mirror. Let's see if I can get convex mirror. Yeah, I gotta go elsewhere. Convex mirror. Spherical mirror simulation. Spherical mirror simulation. Let's see. Convex and concave mirror. Let's take a look at this one. Convex and concave mirror. This one I think you can interact better. Okay. Convex and concave. Yeah, good. Let's see here. Huh. Doesn't make any sense. Convex. Oh yeah, okay. Okay, I am confused here. So here you go. Here's my object, right? But I don't like the candle. I don't like the candle. Let's reflection and spherical mirrors. Let's take a look at this one here. Okay, I like this one better. Here you go. See focal point and center of curvature. Focal point and center of curvature. This one doesn't have much of it behaves just in a single way, okay? So you're always going to have a virtual image for this object that's in front of the mirror, okay? And by the way, let's see, let's take a look here at my simulation, the drawings. Yeah, I could have come up with a third, right? I didn't come up with a third. The third one is the one that passed through the center of curvature. Okay, that's the one. That's the best one. 3 light rays. And all those 3 light rays, they coincide with the. So it behaves mostly like the concave mirror. You use the same light rays, but you have to choose properly. Here, the focal point should be the prime. The prime should be this one here. The prime should be this one here. Okay, because the center of curvature is behind, then the focal point F should be behind as well. Okay, and here will be the prime. Okay, so this one's going to be prime, and the next one that comes is going to be the F without prime. Prime, got the idea. Okay, so here we go. The equations of this is exactly the same as the equations for the concave mirror, but there's a little trick there. Okay, so let's do an example here. Example. I'm going to copy this example right here. Example. A mirror has a center of curvature of -2 meters. Okay, it's a concave mirror. An object is placed at a distance 4 meters, at a distance of 4 meters. Find the position of the image. Okay. Don't forget that's going to be minus the center of curvature is 2 meters. Consequently, the focal point is going to be, focal distance is going to be -1. Here is -1. -1. Oops. -5. -5. -4/5. -4/5. Look here at the eye as being negative. It means that the image is virtual. Okay. No matter, focal point is always negative. If the object is always a real object, this left side will always be negative, and the object will always be virtual. Okay, if D naught is positive, the DI will always be negative. There are ways that the D naught can be negative, but we're not gonna get into that, okay? Otherwise it becomes too complicated, but it's possible to combine lenses to get not just lenses, but mirrors as well, to get a negative, a virtual object, not a real object, but a virtual object. Consequently, for this case, the image will always be virtual for a concave mirror. Concave mirror. And what else can we cover here? The last thing that we have that you have to know. Okay. This is the equation here. The equation of the mirror. This is an approximation, by the way. This is the equation above, the equation below is an approximation of what we find in real life, but it's a very good approximation. And also not just this equation, but also this one here. F equal to C divided by 2, right? This is also an approximation. The equations below are an approximation, are approximations of what we find in real life, but although very good approximations. Now, there is one more equation that you have to know. Okay, and it's in the book. There is the height of the object and height of the image. Okay, there's a relationship we obtain using similar triangles. It's given by, I'm adopting the notation of the book, HO divided by HI. And by the way, it's going to be a negative sign here. Okay, and what else? That's going to be given D of the object divided by minus. No, not minus. There's no minus here. Recall that there is a relationship, okay, between DI or the inverse of DI, right? Using note C that 1 divided by DI is equal, right? The inverse of the focal length minus D naught. Let's see, let's do the substitution here. What happens? I'm going to plug the inverse of the I right in here. Let's see here. And when I distribute the D naught, what we end up getting? The number 1 here. Put in the same common denominator. And we get D naught minus F. Like that. Okay, there is a definition. H naught and HI are the height of the images of the object and the image, right? And now we also have the idea or concept of magnification. What's that magnification? Magnification is going to be the height of the image divided by the height of the object. Make sense? There you go. Magnification M. And that would be F. There must be a negative sign here as well, right? D naught minus F. Even better, I'm going to put this one here, shorter. Okay, here is going to be DI divided by D naught. That's 1135 here. And mirror equation, yeah, the mirror equations here. And that's what we have for this chapter. Fracture of light, mirrors, magnification, yeah. The mirror equations, this one that I put at the beginning, okay. That's here you go. Let's go through the book, right? So you can be familiar with what I'm not gonna ask for wavefronts, okay? Wavefronts and rays. I think that just introduce some complications. Just think of light as a ray that propagates away from the source. Okay, but then we start here with reflection of the light. Angle of reflection is equal to angle of incidence, and there's an illustration that I also illustrated for you in a simpler drawing, right? Less fancy. Here you go, specular reflection, diffuse reflection, formation of image by plane mirrors. And here's the law of reflection. Okay. Here, this guy is visualizing where the piece here of the object is formed. Doing that procedure that I showed to you. Some other examples that you want to go through. Let's spherical mirrors. Okay. That's the ray tracing method. We call it the ray tracing method. Light rays parallel to the axis reflect towards the focal point. Here's the focal distance, focal point, focal distance. Okay, focal length of a concave mirror. This is an approximation. It's half the radius of curvature. Okay. remember that that idea of the focal point applies only for mirrors that has a diameter that's much smaller than the focal distance. Okay, when we go to a mirror, to a spherical mirror like that, in which the diameter is comparable to the focal distance, then those reflected rays don't cross the focal point. That's why I said that that we are using an approximate equation. When it comes to this point, we have to use a parabolic mirror that's going to reflect the light towards the focal point, towards a single point. That's not something I'm going to ask you in the exam. Okay, here you go. Formation of image by spherical mirrors. Light rays parallel, reflects towards the focal point. Light rays to the focal point reflects parallel. Light rays, passing through the center of curvature, reflect towards the center of curvature. Okay, and then you have to know how to form images. Okay, how do you come up to also do that to form the images? And using at least 2 light rays. And here is convex mirror, which convex mirror usually provides an image that's smaller than that of the object. Mirror equation, and that's what we did. The mirror equation is that one that you saw. Here you go. Here's the mirror equation. I showed to you the relationship between, we derived those using similar triangles. Okay, so see, we have one triangle here, we have another triangle here. Those triangles are similar, so we can relate them to each other. Magnification. And that's the James Webb Space Telescope. It's kind of, let's take a searching. Okay, James Webb Space Telescope will be the largest and most powerful telescope ever launched into space. Successor of Hubble Space Telescope. Okay, they each both Hubble are similar in how they operate. They're both mirrors. They each have a large primary mirror. Okay, they reflect this focal point coincides with the location of scientific instruments. While the 2 telescopes operate in similar fashion, is especially designed to view the universe using longer wavelengths, which will be the infrared light. This makes it particularly well suited for analyzing the atmosphere of new exoplanets. So in order to understand the James Webb Space Telescope, you have to understand how mirrors, concave mirrors work, okay? Which are planets that exist outside solar system. Okay, 4,395 exoplanets in 3,242 star systems. Molecules in the atmosphere of the exoplanet that might be conducive to life, such as oxygen, water vapor, methane, have a large number of spectral figures. So I once attended, a presentation by one of those guys that are working this project, and they expected to detect a planet with Earth-like atmosphere in the next 10 years. Okay, so that's what the James Webb Space Telescope might be able to do in the near future. A large number of spectral. So just by analyzing the spectroscopic signal that the telescope collects, you can say whether the planet has an oxygen atmosphere or not. And once you detect a planet with oxygen atmosphere, you can induce from that planet must have plants that produce oxygen. A planet with an oxygen atmosphere is not very stable. If the oxygen is being produced through other sources other than that of a plant, the planet would leach its oxygen atmosphere very, very quickly, because oxygen reacts with all sorts of compounds, right? Even though the telescope will utilize wavelengths of light outside the visible spectrum, the law of reflection will govern how the light will reflect on the surface of its mirror. The primary mirror, James Webb Space Telescope, is composed of an array 18 hexagonal mirrors. Okay, just like a little puzzle of 18 mirrors that are each 1.3 meters in width, making the overall diameter of the primary mirror 6.5 meters. is 2.5 times larger than the Hubble Space Telescope, the mirror of the Hubble Space Telescope. At temperature 30 Kelvin, which will be close to the temperature of the telescope in deep space, the radius of curvature is 15.880. That's the radius of curvature, not the focal point. At what distance from the primary mirror should the secondary mirror be placed if light from far away is to be focused at that location? Okay, so you want the secondary mirror to be placed at the focus of the primary mirror. Okay, it's just half, right? That's the focal distance. And then we have this example. The focal point, the focal distance of convex mirrors is negative, it's a negative number. Remember that. The curvature distance is also a negative number. And I guess that's yeah, I guess we can stop here. Do we have any questions? So we did manage to finish this chapter, and let's not go yet. Let me just make sure that I got your that should be physics 7. Okay, that's physics 7. Okay, so I'm gonna work on your homework number 9 for chapter. Oh, wait a minute. Looks like I was in the room. See here. Yeah, okay, I have to prepare your homework for this chapter, which is chapter 25. Yeah, I will get your homework posted, right? You have here for the electromagnetic waves, and I'll post also the homework for chapter 25 soon. Okay, so we finished chapter 25, and you should study that for the exam. He goes 22 through 25, right? Labs 5 and 6. I'm gonna get it correct. I'm gonna get them corrected before Wednesday. That's what's gonna go for the exam. So 22, 23, 24, 25, 4 different chapters. Okay. So there's no questions. I see you again on Wednesday.